Great. Thank you all for joining our latest webinar on calibration, validation, and confirming gel performance. I'm Abby Lindberg. I lead GelSight's applications engineering team. A couple of reminders before we get started. We will be recording this webinar and putting it on YouTube. And we'll also have the Q&A live throughout. We have Alejandro from our sales development team answering questions throughout, and we'll also get to them at the end. And if you ask a question, it'd be great if you could include your location so that we can have the right person follow up with you after the webinar if necessary. So with us today, we have Kimo Johnson, and I will hand it over to him to introduce himself and talk about how GelSight works in more detail than we've really gotten into before, and then our calibration process and what is that.
Thank you, Abby. I'm Kimo Johnson, co-founder and chief science officer here at GelSight. The GelSight technology is a handheld scanner that can capture the 3D surface of any material and produce a detailed measurement report in seconds. Our ability to measure any material comes from the unique gel sensor at the end of our systems. The sensor conforms to the shape of anything that touches it and reveals a lot of detail. This was originally designed to be like human skin. Your skin is soft, it conforms when you touch things. But with this, we put an imaging sensor behind it and have developed a way to digitize touch. Our system is fundamentally a system that uses a camera to measure 3D shape. But in general, this is a challenging problem because materials in the real world reflect light in very different ways. We know this from our experience looking at all sorts of objects. On this slide, I'm showing a metal coin. It's shiny, and you know that if you tilt it to the light, there are certain angles when it acts like a mirror and produces a very strong signal back to your eye. Human skin, and in this example, fish skin, can be translucent. The light is going into the object, bouncing around and coming out. This is called subsurface scattering, and it affects the appearance of translucent objects like skin. Transparent objects can be even more complicated. This emery board has transparent crystals. The light goes into the crystals, bounces off certain surfaces that are at an angle with respect to the viewing direction, but you can't really see the structure of this surface because the crystals are transparent. All of these challenges make it difficult to measure 3D shape on real-world materials, and this is where GelSight comes in. Let's take the emery board example in more detail. We know from experience it's an abrasive, and if we press the gel up against it, you can see the gel reveals a very different appearance of the surface. It looks like a rocky landscape, which is in fact is what it is. The gel allows us to mechanically filter out those optical properties, replacing them with optical properties that we have designed. This gets into how we can use this technique to measure 3D. Looking at these examples again, you'll see that the gel reveals a very different image. You can't see the subtle structure of this skin because the light is going into it and bouncing around because it's translucent. With the metal coin, the gel reveals a lot of detail that's also difficult to see with your eye. In fact, this 20 micron micro printed word on the coin. But once we've controlled the actual reflectance properties of the surface, we can apply our unique 3D algorithms to do a 3D measurement of the surface topography. And so what I'll describe in the next few slides is to give you some intuition about how this works. The problem of measuring 3D from images is known in the literature as a classic problem of shape from shading. We see a shaded value, which is the brightness of a pixel, and how do we infer that shape? On this slide, I'm showing a sphere, which is a very simple shape, but it's a nice shape for this purpose because it has every possible slope that's visible in the system. You imagine if you're standing at the center of the sphere and you walk in any direction, it'll start to be inclined in different ways. But those slopes are really what our system is measuring, and we're taking the brightness value and trying to determine the slope. Suppose we observe an intensity of 204 at a position in this image. If we look at the shape and we try to determine what the slope is, we'll find that there's an entire ellipse of pixels that all have intensity 204. So there is not a unique mapping from this intensity value to anything about the shape. It's not unique, but it is constrained because that ellipse tells you all the possible slopes that could have intensity of 204. Similarly, at any intensity, there's a different ellipse for each of those intensities. So a single intensity provides some constraint on the surface slope, but it's not enough to infer the exact slope at that position. In 1980, Woodham, a researcher at University of British Columbia, published the first paper on what's known as photometric stereo. Stereo imaging, what many people are familiar with, uses multiple cameras to measure 3D shape. The idea behind photometric stereo is to use multiple light directions to measure shape. Here, I'm adding a different light from the lower right, and you can see that that light creates a different set of constraints on the intensities and their corresponding slopes. Suppose we observe at a single position an intensity from one light direction of 204, an intensity from a second light direction of 153. You have two different constraint ellipses. So where they intersect shows the two positions on the sphere that can have that pair of intensities. It's still not unique, but you've gone from all possible slopes down to only two that could have that intensity pair. If you add a third light at this position, also observing an intensity of 179, the third constraint ellipse shows you there is only a unique single position that has that intensity triple. And this is why in our system we use multiple light directions of the gel to calibrate. So our calibration specimens are a ball grid array, which is really a direct implementation of the process I just described. We also have a flat specimen that gives our system the ability to measure the illumination gradient, how it falls off across the image. And finally, a certified specimen with an XY distance between the center of the two circular features and a certified Z depth. So now Abby will show you how this process works in our software.
Thanks, Kimo. So I'll actually switch my camera over so you can see the desktop here. I've got all of our calibration standards on the desk. Let me share that video. All right, hopefully we can see that now. And we just saw the images in Kimo's slide of these targets taken with the GelSight system, but here are the physical targets. We've got our flat glass target. We've got our ball grid array. And then we have our groove target. We call this the G520 for our Series 2 system, which is what I have on the table here. And this is what is the certified target. So we have a groove here and the two holes on it with the certified depth of the groove and the certified distance between those two features to give our measurements and calibration traceability in those orientations dimensions. And then you'll also see on the desk, I've got our validation plate, which we'll get into in a little bit. We'll start with calibration first. And now I'll go ahead and share my GelSight mobile software, and we'll walk through what the calibration process looks like. And as I share this, just as a reminder, we can, if you want to make the video larger or the screen share larger, you can click between the two and it'll make one the larger, featured video. So you're welcome to switch between video and screen share as needed. So let me click on the software here. And we can see this screen share now. And I've got a gel in here, and I'm going to click calibrate so we can see what that looks like. All right, when I click the calibrate button, the first thing it's going to do is run an auto exposure routine, and then it's going to run an auto focus routine. So we're setting the image brightness, and then we're focusing the lens. And now we're going to follow the prompts on the screen in the software to calibrate the system, or calibrate the gel to the system. So the first one says scan the flat target. I'm going to take our flat target, and I'm also going to take our alignment fixture. So this just snaps on to the front of all of our targets like that to help us align to that target with our system. So I've got our Series 2 here, and I'm just going to press it down through my alignment fixture onto the surface of that target. And the goal for this is really to just make contact in all 4 corners. And I click the button to take the scan. And as Kimo just described, we're doing this to look at the fall off of the illumination system around the edges. The next scan, it says scan BGA 1 of 4. So we're actually going to scan the ball grid array 4 times, rotating it 90 degrees each time. And it doesn't matter which orientation we start in, we're just going to rotate it each time, giving us, redundancy, more and more data points to describe what Kimo talked about in the beginning, looking at the illumination around the spheres. So I'm going to go ahead and take those 4 scans. I'll just press down onto the surface here and click the button to take that scan. We'll rotate it and we'll just keep going. You can see our target has a hole in the center of it. So a bunch of spheres, and then we have a hole in the center. And we use that as kind of a visual indication that you're applying enough force to see the gel conform around the spheres. If that's about 25 to 50% covered with a shadow, you're pressing down hard enough for the gel to conform. And you'll see on the right-hand side, we draw a bunch of yellow circles around those spheres when they're found by the algorithm. And finally, it says scan groove. So we're going to switch over to our last scan for the calibration process, which is our groove target. And we'll snap that fixture onto it like that, and we're ready to take that scan. So for this one, we just need to make sure we're seeing both holes in the bottom of that groove. And we'll click the button to take that scan. And once all of our scans are taken, we can click the calibrate button. So each gel needs to be calibrated before you can use it. You don't have to calibrate the gel each time you connect it to the system, just that one initial time before it's used. However, we have some customers that have a requirement that they need to verify that the system is performing accurately every time they use it, or maybe even every certain number of scans or monthly even. And that's where the validation plate comes into place. So we'll get into that next. We can see a calibration result has popped up here. And we've got anything under 2% error is going to be green. I now have an accept calibration button. Anything over that 2% error is going to be red, and you won't be able to accept the calibration. So I'll just go ahead and I'll click accept calibration here. And now this gel would be ready to use. So I'll actually stop sharing my screen now so we can switch over to validation. And I want to hold up the validation plate with a kind of a larger video display. So the calibration process has to happen for every gel before we can use it. But rather than each time we use the system, since it's not a requirement, we would want to validate. So here we have our validation target. Another plate uses the same alignment fixture as our calibration plates. And this is what we can use to do basically a quick check pass fail if we're still reporting within tolerances. So Kimo, do you think you could talk a little bit about the target design and what we have on this target?
Sure. The validation plate was designed, as Abby said, as a quick check that the system is still operating within its specifications. So on this plate, we have 2 different grooves of a shallow depth and a deep depth. And then we have 3 different circular features where we've certified the distances between those, a shorter distance and a longer distance. And with this plate, we've designed algorithms that can automatically measure all of these features and decide if they're within tolerance. So it's a quick way that the user can check all of those features at once.
Thanks, Kimo. So I'll now walk through the process of what that looks like, or running validation looks like in the GelSight software. So let me share that screen again. And I'm going to click validate in our software here. So validation can be configured as a requirement. So it'll basically make it so that you can't take any scans until you pass validation. And you could set this to be performed daily, weekly, monthly, or after a certain number of scans, so that you can't actually go on unless you're reporting within your tolerances. The other thing we have on this page here is the validation plate listing. So mentioned this plate has the certified depths and distances between those features. And all of those come in an XML file to upload into your software. So when we take the scans of these plate, we're checking what our measurements are against those values from the certificate that's uploaded into that XML file. So in this case, I'm going to go ahead and click validate. We can manually run the validation process. We don't have to have it as a requirement to continue. And we'll click that button. First thing it's going to do is focus the camera. And now we're going to follow the prompts on the screen, just as we were doing with the calibration. So you can see the first step here says scan validation target. We have a 1 out of 3. We're actually going to scan this target 3 times. I'll take our fixture and snap it on the front there. And I'll align our system in here. And we'll press down and take the scan. And I'm going to rotate it and go ahead and take the next scan. And we'll go ahead and we will take a third scan as well. So 3 scans involved in the validation process, and we're rotating it so that we have to check all of those dimensions across multiple orientations and multiple scans. So we're not just checking one time for one measurement in one location. And we can see that this validation was successful. We passed all 3 of these scans. You do need to pass all 3 of them to accept or to pass validation. I can click accept here. I can also export the results. So if I need my validation, all of the numbers associated with my validation process into a CSV file, we can export all of those results here. And we can also mouse over the images, and it will pop up with the tolerance. All right, so I'll go ahead and click accept here. And now we've passed validation and we can continue to take scan. So what does that process look like on a bad gel or a time when we're ready to replace a gel? I'll actually swap this gel out. We'll come in here and I'm going to click add gel. And I'm going to put a damaged gel into the system so we can look at what that process looks like. And we can talk about other indicators for when to replace gel. All right. I'm just going to install this cartridge into the front of my Series 2 system. And I'm going to click validate, and we're going to go through that process again. The first thing that you'll notice after the system focuses is that this gel doesn't look that great, right? So this is definitely an example of failing validation. And before I take the scans, I'll even hold the system up to the video camera here so that you can see what that damage looks like. You can see all that wear through that pigment layer. And now I'll go ahead and take some scans of the validation plate. So we'll come in here, we'll press down. You can even see how the illumination on that gel changes as it conforms into that groove. We'll go ahead and take the next one. And we'll take the last one here. This gel is also pretty sticky, which you might see when I'm pulling it off of the surface. So we can see we've already failed the first scan. So we failed validation at this point. It's going to still run through the process of measuring the other features for all of the scans. But the process for validation failure is to try recalibrating and then validating again. And if you fail one more time, then you would want to replace the gel. So this is what's giving you that kind of quantified reason to replace your gel. And I've got, let's see, I think we've got a couple images of that really highlight when to replace a gel. and maybe when you pass and when you fail validation that we'll pull up here. I'll also switch my camera back over here. So on the left-hand side, of these images, these are ones that have passed validation. So even though you see some damage on the surface of these gels, these are still passing validation. We're still getting measurement results within our tolerances. And on the right-hand side, we're seeing some that fail validation. And you can see there's much more damage. The kind of black or white spots on there, that indicates indicates light coming through that pigment layer. I know, Kimo, you could talk a little bit about the importance of that pigment layer.
Yeah, so as we discussed at the beginning of this presentation, our system is calibrated to the unique reflectance properties of the gel. So if the image is seeing black pixels because there are holes in the membrane, or white pixels because you're getting reflections from the part underneath, you're no longer, satisfying the unique properties of a GelSight system. So the gel needs to be replaced to get you back into the measurements with GelSight technology.
Thanks. Yeah, so these ones on the left-hand side that are failing, there's a lot more light coming through. It's coming through a lot of the field of view. It's definitely affecting our measurement results. These couple that you see on the left-hand side actually end up highlighting that that top left one has a puncture mark through it. And we're kind of highlighting that there is usable space on the gel where we're measuring within tolerance. I probably still wouldn't measure exactly in that one spot where there's a puncture mark, but we're still definitely reporting within our specifications for the requirements of the validation plate. So to kind of summarize what we just talked about, calibration is required for every gel, before we can use it. But who might want to use validation? And that's pretty much anybody that wants to confirm their gel performance in a quantitative way. So rather than looking at a gel here, I'll turn the light back on this so we can see what that looks like again. So without the validation plate, this is going to be a subjective process, which is fine. We're looking at the light coming through this, and I'm going to replace it when there's anywhere coming through the pigment layer. But the validation plate allows us to make that determination through measurement. We also do have a lot of customers that have a requirement that they check that their system is reporting within a spec. And a lot of times that check can't be used, can't use the same target that you're using in the calibration process. So we can't validate on the same reference that we've calibrated with. So really the validation plate is optional. It can be purchased as an add-on for your system, but it really can help you make data-driven decisions about gel replacement. So with that, I think we'll wrap up here and see if there are any questions in the Q&A. It looks like we have one question about the certification process. So it says, does GelSight certify their calibration targets, and do they need recertification? So we use a third-party lab. East Coast Metrology certifies our reference targets. I'll hold them up again here. We've got the validation one and the calibration one. And we typically leave the recertification interval up to our customers. Some of them require that they're recertified at every 6 months. Some of it's every 2 years. But I think by default, we look at it as 1 year. All right, and we'll give everyone a couple more minutes to put any questions in the Q&A. And just a reminder, it can be a little tricky to find in Teams. You might have to click the ellipse to get to the More section to get to the Q&A there. All right, we'll give everyone maybe 1 more minute before we wrap up here. All right, we've got a question that says, how many measurements can you take per gel? And that's a great question. So it is a consumable. You do replace your gel. And it really depends on your application. So we do have a pretty wide range of, a couple hundred scans to 1,000 scans, depending on the applications. So interesting ones might be 1,000 scans on ski edges, or maybe 200 to 300 scans on defects on aerospace components. Kimo, I don't know if you have anything you wanted to add to that as well.
Certainly, it's like your finger. If you press your finger into something sharp, it'll cut you. And if you press the gel up against something sharp, you can cut the gel. And if you're measuring abrasives with it, it'll wear off the membrane faster than measuring smooth parts. So it is dependent, as Abby said.
All right, let's see, we've got one more coming in. Where can I send my targets for recertification? Feel free to reach out to us and we can help with that recertification process. We have some customers that send them back to us, or if you have your own third-party lab that you prefer to use, that's an option as well, but we're also happy to help you with that recertification process. Are those the only 2 items that need recertification? Yes, we don't have to certify the flat target or the ball grid array, just the calibration target and validation target. And we have another question here that says, does the validation plate work for all probes? So the one that we're using today with the Series 2 system will work for Series 2 and will also work for the Max. We have one in the plans for Modulus, but I don't have a date to give you yet. But obviously, we're looking at a much smaller field of view, so it will be a separate target. All right, so I think that's all that we have for questions. So thank you everyone for joining today. And just a reminder, we'll be uploading this to YouTube. So once again, thank you.
Thank you all.